Hello everyone. Welcome to the SWAYAM NPTEL course on Mathematical Geophysics. Today we will continue with Module 4 Mathematical Modeling Part 2. This is the third lecture, Electric Fields. In this lecture, the concepts covered pertain to electric fields. The 5 components of this lecture are as follows. First, we'll look at the basic Coulomb's law. Second, we will discuss the electric field for a discrete charge distribution. Third, electric field for a continuous charge distribution. Next, we will discuss divergence of electric field and curl of the electric field. Now, these concepts have their corresponding applications in geophysics, which also we will be discussing. So, let us begin. The Coulomb's law. The Coulomb's law describes the electric field due to a point source charge, that is Q. The test charge, capital Q, and the point source charge, little q, are placed such that the distance between them is r. Here, little q and capital Q are the 2 point charges shown in red and blue colors. Our aim is to know what is the force on the test charge capital Q due to the single source charge little q at rest and at a distance r away. The force is found to be proportional to the product of the two charges and is also found to be inversely proportional to the square of the separation distance. Which means that force is proportional to Q and capital Q and inversely proportional to the separation distance. This is mathematically shown here. Now, this is based on the experiments conducted by Charles Augustin de Coulomb in the 1718s. The force is given by F vector, which is the force field, equals 1 by 4 pi epsilon naught q capital Q by r square r vector. This is a constant quantity where epsilon naught is the electrical permittivity of free space. Its value is 8.85 into 10 to the power minus 12 c square. Its value is 8.85 into 10 to the power minus 12 Coulomb to the power minus 2 Newton to the power minus 1 meter to the power minus 2. This is in SI units. Now, here we have the product of the two charges. This is the separation between the charges. This is the unit vector pointing along the separation distance. Having understood the Coulomb's law, now we move on to the electric field that is formed by a discrete charge distribution. By discrete charge distribution, we mean that the charges are point sources which are located at distinct locations without any connection between them. The several point charges are denoted by Q1, Q2 up to Qn. These are at corresponding distances r1, r2, etc. from the field point capital P. Now, this is clarified in this diagram. We have the Cartesian coordinate system with origin at O and the x, y, z axis. The field point P is the point where the electric field is to be estimated. The red dots are discrete charges. One among them is Qi, that is the source charge highlighted here. In general, these charges are denoted by Q subscript I. Now, for the general charge Q subscript I, the distance is R subscript I. With this in mind, we can look into the total force as F vector equals F1 vector plus F2 vector and so on. These are the individual electric fields or electric force fields which are produced by the individual point source charges on the field point Q. We have used P and Q interchangeably here. The F vector now corresponds to the sum of the individual source fields. Having taken the component which is constant outside as a common factor, we have the rest of the expression given by Q1 into Q by R square, which is R1, plus Q2 into capital Q by R2 square, etc. This simplifies to F equals capital Q by 4 pi epsilon multiplied by Q1 by R1 square directed along R1 vector plus Q2 by R2 square directed along R2 vector and so on. Now, having performed the vector addition, we get the resultant direction of the electric field E vector. Thus, the force is given as capital Q into the electric field, that is F equals QE. Thus, E can be summarized as 1 by 4 pi epsilon summation over all the point charges Qi, where I ranges from 1 to n. Upon performing the vector addition, we will get the resultant direction of the electric field E vector. Now, E vector, as can be seen from this expression, is the electric field due to the source charges. It depends only on the source charges. It does not depend on the test charge capital Q. Thus, the electric field is proportional to the source charges distribution and inversely proportional to the square of the separation distances between the source charge and the test charge. Now, we will have a look at some special cases of the electric field distribution for discrete charges. For simplification, let us consider that the total number of point charges is limited to 2. Now, these two charges are placed at certain distance among them. They form a charge couple. Note that the charge are of the same sign. Both are positive charges. The field lines are shown here. Recall that we have looked into the field line concept in the geometric representation lecture, and we had seen that the field lines interact among each other and get distorted from the original individual and independent field lines, which can be caused by the individual point charges. This results in the distortion such that the effective field lines become as shown here. Now, suppose the charges are of opposite sign. We can see the dramatic change in the geometric representation of the field lines. This is a dipole configuration where we can see the field lines emanating from positive charge and converging on the negative charge. Whereas in the case of the coupled charges, the field lines tend to move away from the opposite charge field lines. We can also analyze various other forms such as the curl and divergence of the field lines as we will look in later part of this lecture. Next, we have the electric field of a continuous charge distribution. Now, continuous charge distribution means that we have charge at every point on the space. So, to denote such charge distribution, we need some concept of continuous charges. Thus, we have the assumption charge is distributed continuously over some region. Now we look into the electric field which is obtained for such continuously distributed charges. With the help of these diagrams, it would be very simple to understand this. The gray shaded area is a continuous distribution of the charges where an elementary charge is shown as dq. Now this continuous distribution is at a distance r vector from the test point P. Our aim is to find the electric field which is generated due to the continuous distribution. As we have seen earlier, this electric field does not depend on the test point P. It only depends on the charge distribution and the separation between the charges and the test point, that is R. Along the same lines as a point source charge distribution, we can get the electric field for a continuous distribution of charges. Now, that is given by 1 by 4 pi epsilon naught integral dq by r square r vector. Now, we can understand this from a simple analogy. Have a look at this expression. We have the common factor 1 by 4 pi epsilon and followed by a summation. Now this summation is occurring because the charges are discrete points. For continuous charge distribution, the summation sign is replaced by the integral sign. This is because now the charges have become essentially a conglomeration of elemental and infinitesimal charges dq. Thus, the integral of dq by r square is essentially representation of a discrete source charge representation as shown here. We can go further to look at some simplified and special cases. First, a line charge distribution. A line charge distribution can be depicted in diagrammatic form as. Here we have a line where an elemental part is shown by dl. Now, the continuous charge distribution can be represented in the form of the line charge density. The line charge density is nothing but the charge per unit length, which is lambda. It means for a unit length, the total charge along this line is lambda. Then the elementary charge distribution in dl becomes dq equals lambda into dl. Thus, at the test point P, which is located at a distance r away, the total electric field due to this line charge distribution is 1 by 4 pi epsilon integral lambda dl by r square into r hat. All we have done is replacing dq by lambda dl. Next, we move on for a source. Next, we move on to the distribution, that is a surface charge distribution. The surface charge distribution is depicted as this diagram. Here we have a surface where an elemental surface is shown as ds. Now, the density of this surface charge distribution is given by the charge per unit area, that is equals to sigma. Thus, the elementary charge distribution in the ds elemental area now becomes sigma multiplied by ds. Replacing dq by sigma ds in this expression, we get the electric field due to a surface charge distribution at a test point capital P, which is located at a distance r from the source charge distribution. Finally, we will look into the most general form of a volume charge distribution. The volume charge distribution is depicted here. Here we have the volume capital V, in which an elemental volume is dV. Now, the charge density is given by the charge per unit volume, that is rho. Thus, the elementary charge distribution becomes dV. Now, the elementary charge distribution in dV becomes rho into dV. The electric field of the entire volume charge distribution can be obtained by simply replacing dq by rho dV in this expression. Thus, we obtain the electric field for a volume charge distribution as 1 by 4 pi epsilon integral rho dV by r square r hat. Thus, we now understand how to obtain the electric field for any charge distribution, whether it be continuous or discrete. We can also use both the expression for obtaining electric field for a mixed charge distribution which contains point sources as well as continuous charge distribution by just the summation of this expression and this expression. Now we look at the divergence of the electric field. To understand the concept of divergence of electric field, we look into the flux of an electric field. As we had discussed in earlier lectures, the flux actually means the extent or magnitude of the field lines crossing through a particular area. Here we have the total area denoted by capital S and an infinitesimal area ds. The ds vector is the normal to the surface S and is shown here. The electric field is E vector. We can see the crossing of these field lines through this surface. Now, the flux is given as integral E dot ds. This is the flux of the electric field. Now, this flux of this electric field is equals to the Q enclosed by epsilon naught. Here, Q enclosed denotes the total charge distribution which is enclosed within the surface. This can be obtained using the Gauss law. This also represents the integral form of the Gauss law or the divergence law for the electric field. We can also understand this from the differential form of the Gauss law. Applying the divergence theorem on the left-hand side of the above equation, we obtain integral of divergence of E dV, which is equal to integral of E dot ds. That is equal to integral of rho by epsilon naught dV, where rho is the volume charge density and dV is the volume element. So rho dV provides the Q enclosed. Upon equating the integrals, we obtain divergence of E equals rho by epsilon naught. This is the differential form of Gauss law. Next, we consider the curl of electric field. The curl of electric field can be obtained as follows. We will be using the line integral of electric field from point A to point B. This is in the same lines as obtaining the curl of gravitational field, which we have seen in previous module. Have a look at this picture where we have a loop starting from A ending at B. Here the Cartesian coordinate system is used where Q is located at origin. Now the distance between this charge Q from any point on this loop is given by RA to RB. This is the variable R, which gives the distance between the charge Q to a point, general point along this loop. Thus, the circulation integral E dot dl along this loop is given by 1 by 4 pi epsilon integral Q by R square dr integrated from A to B. This is simplified to 1 by 4 pi epsilon Q by Ra minus Q by Rb. To obtain the circulation around a closed path implies A and B becoming coincident. This completes the loop but also means that A and B are equal. Hence, Ra becomes equal to Rb. Now we have the right hand side of this equation going to 0. Thus, integral of A to B E dot dl equals 0. This means that the circulation of the electric field around any closed loop equals 0. Applying Stokes' theorem, we can obtain that the curl of the electric field equals 0. This is because the integral E dot dl is equals to integral curl of E dot ds. This integral must be obtained over the entire surface enclosed by this loop. By the property of curl-free fields, we can obtain that the electric field is a conservative field. Thus, we can conclude that electric field can be used for various geophysical applications as it is a conservative field. In particular, it can be stated that certain geophysical applications make use of the electric fields. For example, the resistivity survey. The resistivity survey is a geophysical application for understanding the subsurface resistivity distribution. This is obtained by injecting electrical current into the ground through electrodes, which are nothing but points where the electric current are measured. The resulting voltage helps to determine the underground electric field distribution. The distortions in the electric field distribution helps map groundwater aquifers and locate mineral deposits and assess soil contamination. This is possible because all these factors affect the electric field. Also, in induced polarization, which is another geophysical technique, the delayed response or polarization of subsurface materials to an electric field is used. The subsurface materials distort the response of electric field. This is then utilized to detect possible anomalies that can be substituted for possible minerals. This helps in exploiting minerals and especially in clay-rich zones. One can have a look into the following references for more details. We will look into further applications in next lectures. Thank you.